maybe let's get started with a tiny example. Let's see if we can run a small example. Well, my question is, do you think we use a single photon, or do you think we use many photons?
Well, so I was saying if they're the qubits, I'd imagine you need many. And then I would also imagine you probably can get averages by repeating the same setup many times with many waves of photons.
So from your answer, I heard you need a single photon as a single qubit, which is actually not true. We actually use a lot of photons per qubit. So this is a common misconception that every photonic technology uses a single photon approach. That's not true. Some of them do, but as for example, we use a many photon approach.
Is that for fault tolerance or is that for something else?
That's just because the way we build the quantum states that we need, and not only for fault tolerance, even for the devices that are currently online. The way we build those specific quantum states, we need many photons. Other technologies, other companies use single photons, but for us, it's much better to use many photons. Does that answer the question?
Yeah, I mean, it'd be good to know, at some point know more about that, but don't want
Yeah,
to.
you can ask. You can. Also, remember how I told you that we had this fiber and we put that laser light in, and we use that chip to modify the state, the way that laser light behave. So if you have many photons, if you have just a laser light, you can describe it in a certain mathematical way. It has a certain state. But if you make it pass through those small corridors, imagine you have a crowd and you make it pass through small corridors, the way you describe that crowd is different, right? And so you can modify the state of those, that light, those many photons, just that pulse of light, you can modify it. So that pulse of light becomes like your qubit. And so it's not just continuous light, it's like small pulses of light. Imagine you have your laser and you turn it on and off. So you generate many pulses of light, and each pulse of light, which contains many photons, it's the pulse itself that describes your qubit.
Thanks.
All right, so let me just something.
We have two other questions.
Oh, maybe you can read them out loud.
Okay. Are there libraries for quantum chemistry in PennyLane?
Yes, absolutely. Absolutely. So do you use, for example, PyCF? We can connect to that. Quantum chemistry is, again, one of our main areas of research because we focus on understanding better batteries. So if that is interesting to you, this is definitely a good place to go. Totally.
Okay, thanks. And the second one is, can you explain more of the photon modulator?
You already answered that question. Thank you.
Okay. All right. So let me see if I can run something. Let me open a you're gonna see whether I fail or not. Let me now share terminal, which has a bunch of stuff, but let's see if I can run. So I'm gonna create a new script. So we're gonna call it like ex01.py. And we're gonna start with something simple. So we're going to import PennyLane SQML. Typically, we imported SQML for historical reasons. So we're mainly based on, doing quantum machine learning when we started. We were really good at that, but now we do so much more, including quantum chemistry. But for historical reasons, you're always going to see that PennyLane is imported as QML very often. And now we're going to import from PennyLane, from PennyLane. We're going to import NumPy as NP. So this is a wrapped version of NumPy, which has some cool extra stuff. And we're going to create our first circuit. So we're going to start with defining a device. So for that, I'm going to say dev equals qml.device. And here I'm going to say lightning.qubit. So this is our CPU device, lightning.qubit, and I'm going to say wires equals 2.
Sorry to interrupt, Catalina. We can't see the top of the screen.
Oh.
Yeah,
Is it better?
that's better. Yeah. So this is okay, sure. So we can just copy this while you're doing it.
Yeah, exactly. The goal, my goal is that you do it. This is why I do live coding. It's because if you just copy paste, you won't understand what's going on. That's why I'm live coding. So we first import PennyLane SQML.
Yeah, thank you.
Then from PennyLane, import NumPy as NP or PNP. You can use PNP if you prefer. Do not confuse it with the other NumPy. And then we can start. So first thing we do is we define a device. It's, in this case, a simulator, which is Lightning Qubit. It's where you will run your quantum circuit. Then we will create our Q node. So I mentioned that this was very important for PennyLane. So we're going to say at qml.qnode, and we're going to add the device. So parenthesis device. This is a decorator that will decorate the function that comes right after it, which is our quantum circuit. So it will tell our quantum circuit that it has to run on that particular device. Now, we define your circuit as a Python function, def circuit or my circuit or however you want to call it. In this case, we're not going to add any arguments to the circuit. And we're going to start by creating entanglement. So we're going to add some gates. You add them just by putting them here, the function. QML dot, we're going to start with a Hadamard gate, which was that H gate that we saw before. And we're going to add QML, I'm sorry, I did forget something. We have to say on what wire it is going to run. So here comes something very important. Well, there are 2 wires, which are the 2 qubits. Remember I mentioned those horizontal lines are those qubits, but we call them wires. That Hadamard is going to be in wires equals 0. So they are 0 indexed. The first wire is wire number 0. Now we're going to add a C naught. So qml.c naught, all capitalized. This gate, as I mentioned, it acts over 2 qubits. 1 qubit is the control qubit, which if it's 1, then it changes the value of the second qubit. So wires equals square brackets 0, 1. What this means is qubit number 0 is going to be the control, and qubit number 1 is going to be the target. That's the one that's going to change. And now we're going to return a measurement. So as a measurement, I could return, for example, the probabilities of each of the possible outputs of the circuit. So I'm going to say qml.probs. And now I'm going to print the output of running my circuit. All right. Let's see. Let's see what we get. Let's see if I did everything right or if I forgot any of the steps. EX01.pi. I'm sorry.
You have to do Python 3.
Thank you. And I did forget one of the steps again. Okay, sorry. I'm on my Scratch and I did pull this, I think. It already exists, yeah. I'm in the wrong place. Going to use bash C, maybe. Maybe that's what I need. Yeah. I need to use singularity exec, etc. Right? I need to
Yeah,
change
that's
this.
right. I was just typing that for you. Yes, exactly that.
So we're gonna use ex01.pi. All right, so it did run. Oh, perfect. For the people who got it running on the notebook, that's great. I'm going to show you how to visualize your circuit. So I'm going to show it here in the not so nice way, but before that, let's analyze the results. You get 0.5, 0, 0, and 0.5. So why do you get 4 answers? Remember how that output of my circuit was a classical number, 0 or 1. And I have 2 qubits. So my possible, a space of answers is either both are 0, or the first one is 1, or the second one is 1, or both of them are 1. So what I see here are the probabilities of each of these 4 possible combinations of outputs. So I have a 50% chance of both qubits being 0, and the 50% chance of both qubits being 1. So what is really interesting here, and what shows the entanglement, is that if you measured one of the qubits, let's say you measured qubit number 0, you would immediately know that the other one is also 0. Because there is no way, there's 0% probability in an ideal world, 0% probability that if the first one is 0, then the second one will be 1. Yeah, so this shows the entanglement. The states are not separable. That is what entanglement means. You cannot represent the system as two separate states. You have to represent them as something that is all together. It's they're both 0 or both 1. Now, let me go back to the exercise, and let me show you how to draw your circuits. So I've printed the output, but I can also print in my case, I will print qml.draw of circuit. Then right after that draw, so I mean, I've passed circuit, but I also have to pass whatever arguments it takes, in this case, none, so empty parentheses. And now I'm going to run this again. And after a couple of seconds, we should see the answer. And for you, if you're running perfect, so if you're running on a Jupyter notebook, you can see this either as ASCII, which is what I will get. I get it printed as ASCII, so you see an H, and you say kind of like the dot and the X, which represent the C naught. So the X is also a way to represent that naught. Or in your case, let me show you how you would print it nicely on a Jupyter notebook. So instead of using this print qml.draw, I don't need that print statement. I could just have qml.draw underscore MPL. qml.draw underscore MPL of your circuit. So let us save this. In my case, I won't get anything. I might get an error, but it won't get printed here, right? But if somebody is in the Jupyter notebook, you will see that you get a nice picture of the circuit printed out. So how are we doing so far? Do you want me to go back to the example? I would like to go to some more advanced examples. I know that we're running out of time, but let me know how you're doing, because it's important that you get the basics right.
My session ended, so I'm just trying to start my session again.
Okay, all right. Yeah, this is very cool. So maybe let me show you something else that we can do. So let me stop sharing here, and I will share some code that I have, some code I wanted to show you today. All right. So I created a quantum machine learning example. So in quantum machine learning in general has two important things. First, you need data. And second, you need something quantum-y related to it. So it can be either a quantum algorithm, it could be quantum data, it could be you're using machine learning to improve the workings of a quantum computer. So all of these are quantum machine learning. But the one that we're more used to are we have some classical data and we put them into a quantum algorithm. So that is the most normal concept of what people understand when you say quantum machine learning. So you have to start with some data. In my case, I created some data points between 0 and 2 pi, equally spaced, and they will follow a sine function. So let me go to the bottom. They have a specific model, which is a sine function. And this is a toy problem. I'm going to try to predict the model in my data. So I create some test data as well, because I don't want to cheat. I don't want to test on the exact same training data. I just shifted it a little bit. In this case, I used default qubit, but you can use Lightning qubit, for example. You can use Lightning GPU, and so that's it's going to be the second example, how to run something using a GPU. Or Lightning Cocos, etc. So Lightning Cocos will allow you to run on AMD GPUs. Now you can create a quantum circuit. In this case, I have a quantum circuit that takes parameters. It takes X and some parameters that I could just call parameters. X is my fixed data, and my parameters are just some parameters that will change after every iteration. I have two gates. an RY gate and a rotation gate. And so that second gate is the one where I'm going to modify those parameters after every iteration. And in this case, I measure an expectation value. So I'm no longer measuring the probabilities. I'm getting a single number as an output, the expectation value of this one qubit. In the end, I create a cost function. I have a loss function as well, because I want to optimize the results for the entire data set, right? For the entire model. So I create a loss function that will help me to the mean squares, basically. So this is not super important stuff, so you don't have to remember this, but it's just to show you kind of something that you can do. And finally, I use gradient descent. I use a gradient descent optimizer. I choose a number of steps. Let's say I choose 100 steps, and I can see the cost gets lower and lower. And what this shows is, well, I get an optimized version of my parameters. So after my optimization, what I obtain is a set of parameters. It's a tensor with 3 values, param 0, 1, and 2. Or it's a numpy array in this case, I think. So I get 3 values that are now optimized that will allow my circuit to predict the output, given that the data is following the same model. And so with that test data, what I do is I can just plot it and see how the x's are the predictions of my circuit. So I am running my circuit for my test data and the optimized parameters. And I get that the circuit can indeed predict the value of that test data. Now, this is a toy example. If you change this to a different sign function or to some other function, it will not be able to represent the complexity of the data. So if you change this to be an image data set, this will not be enough. But it shows you how, like, the minimal example of how quantum machine learning problem can work. So how you can, use data and use a quantum computer and train it to find the optimized parameters, giving a specific cost function that will help you find the solution to a problem. So in this case, we wanted to model the underlying model in our data. And this was just to show you, if we use the PennyLane style, just a specific PennyLane drawing style, PennyLane has a very particular style. Now, if we want to use GPUs, for example, so in this case, actually, let me share the other screen, which was the let me share the terminal. Let me share the terminal here. So in this case, okay, here we are. Do you see it properly, or do you see everything? I don't know if you still see everything or just a part of it.
I can see it.
You can see everything? Okay, perfect. So in this case, what if we don't use Lightning Qubit, but instead we use Lightning Cocos, for example, right? So what if instead we want to use a GPU? We could totally do that, and it's just as easy as changing this device. Now, using GPUs is slower if you're using less than 20 qubits, because there are some overheads in running them, right? So if you're using less than 20 qubits, you might see a slower behavior in using those GPUs. So they're, again, use them when you need them, when you have a lot of qubits, when you have high depth in your circuits, etc. So here we're going to see that it might be running a little bit slower than what we had before, but we should be able to run the example on Lightning Cocos. So it might take a while. Oh, and it won't print the circuit, but that's okay. Something that I would recommend is, for example, when you want to create those large circuits, you can use something called templates. So maybe in the next session, in the Q&A session, I can show you how to use some of those templates. So you can have one that creates a lot of entanglement, and this can allow to create these more complex systems that are harder to simulate on a classical computer.
So Catalina, I was just going to say that it might default to the CPU because you're running on on the login node. The login node doesn't have a GPU. I'm not too sure what the Cocos backend what it does in terms of defaulting, but for people who want to try, you do have to ask for a GPU node with some GPU reservation and some GPU nodes, and then it will really run on a GPU. So in the S bash script for the Jupyter notebook, you'll see there's an explicit request for the GPU nodes, a single GPU. If you kind of replicate that request with SLOC, then you'll get an interactive session running on a GPU node. And then if you then run srun singularity, so the same thing that Catalina has, but with srun in front, that will then run the container on the GPU node if you have the appropriate singularity module loaded. So there's a bit more work to run on the GPU nodes because we've got the login nodes don't have GPUs.
That's normal. So the key thing is at the level of the code itself, it's very easy to change, to run, whether it's on a CPU simulator, whether it's on a GPU. You can then add, the stuff like you're experts in HPC, so you can change the number of threads, for example. This is something that you can use in order to try to optimize the circuits that you're going to run, like to try to optimize the resource use. There are different things you can try, but the first thing I would recommend would be, if you're running large circuits, try first with the CPU. If it doesn't work, like try a GPU. So if you have over 20 qubits, then that's where a GPU will become useful. And you very quickly will realize that 20 qubits is not a lot. For hard problems, 20 qubits is really not much.